Where is she trying to
take
take
crash,
us?
and I was trying to.
Okay.
And tried to take me to the.
Dude, I straight inhaled a lifesaver.
Okay.
I was wondering if I was going to have to give you the Heimlich.
So, if we want to build something like this, you could build something like this very easily by just making an array, and then every time you wanted to find it, search through it to look for it, right? So we could implement this in a variety of ways. One way that we could implement it is we could implement it as an array, and then finding one of these things becomes a linear search operation, which means it has big O of n to look for it. So if I have 120 records, I might have to do 120 searches to find something. Even more importantly, I would have to do 120 searches to validate that something wasn't in there. And that would be bad, right? Because then I'd do n searches in the worst case. I could implement that also as a search tree. And really, if I was going to do this, I would use an AVL or a red-black tree. Now in that case, and I should mention that insert in the array, inserting takes constant time. You just pick the next slot in the array, right? Boom, right there at the end. Or if you have a vector that constantly expands or something like that. Well, there's that. So I could have a search tree. With a search tree, the find operation, remember what the find's runtime was in a search tree?
Log in?
Log in. And then insert would also be log in, which means that insert is better in the array because the array is constant time. But we could do that. We could use an AVL tree to implement something like this. In fact, it might not be a bad implementation. In fact, most of the time, when you get these data structures, they are not implemented that way because there's something even better. Most of the time, it's better. Okay, and so the other possibility is what's called a hash table. That's what we're going to talk about tonight. Now, the thing about a hash table is that we can't really prove what the real algorithmic complexity of it is. But if we do it correctly, then the average case is constant to find things. Now, the worst case to find things is big O n. And then insert the average is also constant. And the worst is big O n. So it means it will never be worse than an array. It will almost always be better than an array. And in fact, there are heuristics that we keep track of so that as it starts to become like an array, then we can make it better again. Okay, so in a practical way, these are faster than the AVL trees. Although the AVL trees guarantee you that this operation will always be done in log time. Okay? Now there's another consideration to take into account too, which is that most of the time these keys are things that are expensive to compare. Like strings are expensive to compare. You have to compare character by character in a string. So if I have strings that are 50 characters long, they take 50 steps to compare. So we have to keep that in mind too, that hashing can be a little bit more efficient. Okay, so here's what the idea about hashing is. So whenever we hash something, hashing takes 2 steps. Okay, so well, first of all, let's just talk about what a hash is. So we have a hash code. This is a function. I'll say it's h of x. This translates h of x into some other range or some other thing, so into some value. Usually x is some complex type, like a string or an integer or a double, although integers aren't really complex, but some complex type that's expensive to compare. The other side of it is the some value, the hash code itself, the output of h of x is usually some integer. So we take something difficult to compare and we turn it into something that's easy to compare. So for example, we might say that if we had maybe the domain of all possible strings, and then we had integers, then h of x would be a rule that can take a string and give it to a corresponding integer. But of course, there are going to be collisions with this. Okay, so the idea is that we can take something like a string or maybe like a double. Doubles are actually more expensive to compare than you think. And then we can turn them into simple numbers that we can then compare. We translate it into something else so that we can place them somewhere. Okay, so this is used in more than just building hash tables, by the way. This is the way that a lot of applications store passwords. Okay, so if I go into /etc, there won't be any passwords in here. This is all the accounts that are on the system. Let's see here. Oh, shadow is only accessible by root for some security purposes, although there's not a whole lot we can do with their values. Let's go somewhere where I have root.
Oh, so like the hash password or whatever? Like the really weird looking strings.
Yeah.
Apparently those like aren't they like really easily crackable though? Like some hash passwords or something?
Not really.
But
Oh, that's not. Okay, so you can go together.
watch some videos from like the computer file guy about that stuff.
Don't believe
Yeah, pretty
on the
easy.
internet.
Yeah.
So if I go to, let's see, if I go cat and then shadow, then we can see the actual hashes here. So this is the password being stored as a hash. So what's happened is a hash code has been computed and that's been mapped back onto the numbers. These are actually base 64 representations of very large numbers that the passwords have generated through. It's a problem that's very easy to work forward, but not very easy to work backwards. So given the hashes, you could in time take these apart if you were able to get at the hash file. They used to be public in the password file, but then it was discovered that you could maybe compromise a hash a little more easily than people thought. I could never ever recover what these people's actual passwords are, but I could come up with strings that would hash to the same values. And that's a thing called collisions. So this uses a hashing sequence called the SHA-1 hashing and the base 64 encoding of SHA-1's hash, which is what Linux uses by default for hashing its passwords. The system doesn't store the password in clear text anywhere. It doesn't even store the password in a recoverable way. When you log into a Unix system or a Linux system, what happens is your password is hashed, and then it's compared, the hash value is then compared against the hash value in the database. When you write a web application, you never store users' passwords unless you're an idiot. which a lot of people out there are. But you don't store passwords, you store hashes. And then when they try to log in, that they hash the string and then they give this. So it's another way, it's kind of a way to secure things, although that's not the kind of hashing we're going to talk about, but it is used that way. It's also used for things like non-repudiation. You know what that would mean?
Nope.
So if I send you a file, say it's something that's critical and you're going to, like a piece of software, and you're going to install it on some kind of system that has sensitive information on it, then you probably want to validate that it really came from me. And so one way that that's done is that I would take the software and then I would generate a hash, and then I would encrypt that hash code, and that hash code would be encrypted with a key that only I possess, and then you would possess maybe a public key that can decrypt it. So everyone in the world can decrypt the hash, but only I can encrypt the hash. So when you get it and it successfully decrypts and the software matches it, then because you run the hash on your end, then that means that it was transmitted correctly, that the hash really came from me, and that the software hasn't been tampered with. In other words, viruses haven't been introduced. If you've ever seen signed applications or secure boot or things like that, that's how that works. And it's not. And some people were all freaked out about secure boot too, because they said, oh, they're going to set it up so that only Microsoft can sell an operating system, and their BIOS will reject anything not signed by them. That's not the way it works. When your operating system is installed, it actually tells the BIOS, I'm installing an operating system that has this key associated with it. And then the BIOS checks the key at boot time. And if it doesn't match up, then it won't let the operating system boot.
Oh.
That's what secure boot is. And that's accomplished through these kinds of functions. Okay. Now there are ways to beat that. No, I shouldn't teach you how to beat that. Well, here's how you do it. So let's say that I've got some piece of software that I've somehow intercepted and I know that it's been cryptographically signed. I cannot re-encrypt the hash in a way that the end user will be able to decrypt. So if I tamper with the hash, they'll know something's up. But what I can do is insert my payload virus into the software and then pad the software with random numbers until it matches the hash again, and then transmit it. It's called a birthday attack. And it's actually too easy to do it. It's like scarily easy to do it.
Huh.
So, yeah. But anyhow, that all depends on collisions. So we talk about hashing. There's another thing where we talk about collisions. Okay, so collisions are where you have two different X's. That produce the same hash code. So if I have two different values and those two different values result in the same hash code, that's a collision. And that means that that hash is not absolute. Okay, for example, one of the earlier hashes that people generally use is one called MD5. You ever heard of that one before? MD5 sum. There's actually one simpler than MD5, just a checksum. You just simply add up all the bytes in a file and say the checksum should be this. That's great for detecting whether or not you've transmitted a file over something noisy. Like if you look at the old Altair programs that loaded off of a cassette tape, their loader would add up all the bytes they were receiving, and at the end of it, the checksum had to match the checksum that came from the tape. I mean, there's no man-in-the-middle attack there. There's a cassette player, and there's the computer, and they're just checking to see if static interfered with the bits that it received. And if it did, then it wouldn't pass the checksum. Well, MD5s are a little bit more than that. If I do an MD5 sum and I give it a file, it'll spit out a very long hexadecimal number. And so that is this hash code applied over the entirety of that file. The MD5 is a very complicated way to hash, and we wouldn't build a hash table using that. This is used for verifying transmission of information. Problem is MD5 sums actually have a very high rate of collisions. So the birthday attacks are very easy to do with MD5s. So they're really only used for, I've received this thing from a piece of medium or a website or something that I trust, and I want to know whether the network was doing okay when I downloaded the file. It's not as much of an issue now, but it used to be that if you downloaded, like, say, a 1 gigabyte file, well, it would take about 2 days, but the other thing was that there was a high probability that some of the file would get corrupted in transit. So you would do this at the end to verify it. Or if you're really paranoid, like say you're downloading something like Tails, or Tails.
No, I forgot what it was.
So it's the Amnesiac, the Amnesiac Incognito live system. It boots up and then it gets on Tor and routes all of its traffic over the dark web. And it runs off of a flash drive, and then it actually does a secure erasure when you shut it down, so that if forensic analysis is performed with the RAM chips, none of the data that you were exchanging can be recovered by any known forensic technique. When you download that you're using a high degree of trust. And so you have to download it and then get those checksums and then check those checksums. So then you can build a circle of trust, and there is a large circle of trust on the dark web that actually verifies the checksums through something like 200,000 or 300,000 independent sources. So if you really, really want to, you can really make sure that you got Tails. Yeah. But anyway, and I always like people are like, they worry that they will get Tails from like the NSA, and I keep pointing out to them that Tor was invented by the NSA. They're using the NSA's network. And they don't like that very much.
Is it like Shaw?
It was made by the Navy, I believe.
Yeah, SHA-1 is one of the more common ones. And if I run that, you see it's got more digits, which means it has more bits, which means it has more entropy, which means that it has fewer collisions. I'm not going to go too much into entropy and that kind of stuff. There's a whole lot of interesting things about information theory that follows from that. You can go look up stuff that Claude Shannon wrote if you really want to know about entropy. One way that you can think about entropy is it's the minimum number of bits needed to transmit something. Okay, so if I said that something had, say it had 2 bits worth of entropy, that means that I'm talking about 4 things, 0, 0, 0, 1, 1, 0, and 1, 1. That has 2 bits of entropy. That's why my passwords are all huge. Because you know the passwords that, if you require like password of 6 to 10 characters, and then you require them to mix and match uppercase and lowercase and special symbols, that doesn't have very much entropy in it at all. I mean, you have an alphabet of maybe 63 characters that people can produce on their keyboards, and then take that over 6 steps, and that's 63. We'll be generous and say 64. The log base 2 of 64, what's the log base 2 of 64?
2, 4, 6. Or like 6, 8, 8, 32. Is it 6?
It's 6 bits of entropy. It's 6 bits of entropy for each one of those characters. And then so I've got 10 of them maybe, so that's 60 bits of entropy. But if I were to make a password that consisted completely of lowercase letters and spaces, then that's 27, where each character would then carry, if you round, well, it would carry 4 bits of entropy per character, a little bit between 4 and 5. I'll say 4, but then I make it 100 characters long, and that's 400 bits of entropy. Which means that your 10-character password that's difficult for you to remember and that you probably wrote down on a sticky note somewhere that a janitor could be talked into finding. And I'm not meaning that hyperbolically either. I used to work in penetration testing in Nashville, and I was one of the site penetrators. And I usually never had to go on site to do that. It was basically like an industrial spy. But we were paid to do audits of companies, and janitors were my best friend. So I would call at like 10 o'clock at night when I knew the cleaning staff were in there. So I'd case the building for a couple of days and learn when the cleaners went in. I would call them and say, I can't log into my system. I wrote it down on the sticky note under a keyboard. Can you go to my cubicle and check? And I'll give vague descriptions of where my cubicle is, and he'll go look. Oh, you must be in the wrong one. I actually got one of them to flip over like 30 keyboards for me until he finally found the password. And I said, oh, that's it. Thank you very much.
Oh my god. That's dope.
Yeah. So anyway, and the other part of if you ever do that kind of work, which is a weird thing for computer scientists to ever get into, is mainly about being a con man more than anything else. Dress up like a janitor. You can go anywhere. Because if you're wearing a jumpsuit and carrying a mop, you're invisible.
Huh.
here for the thing.
For the thing.
No, I'm serious. There was a company in Nashville, which was a government contractor, and the work that they did actually had top secret clearance in some places, and I got into their secure area. And I did it by rolling up with a bucket and a trash can on wheels, and I said, "Can you buzz me in?" And then I went.
What if you were a Russian spy?
Exactly.
Yeah.
And then at the end of the audit, when they traced my path, they said, "You probably caught me on a bunch of security cameras." I told them when I came in. They said, "Let's go look." And they observed the fact that I walked from my car in the parking lot. The security cameras watched me pull out the thing. It's an empty trash can, stick a mop into it, walk from my car into the building, get into the elevator, go up to the floor, and I walked straight to the security guard and said, "Let me in," and he did. So,
Oh man.
of course, before you decide to pursue a career in this, they didn't always work as well as that. Like one company actually found that they were actually pretty good. I had gotten into their server room. I was copying hard drives, and someone noticed me doing that. They locked the doors
Huh.
and then called the police.
Oh my God.
And they told me that they had called the police. So then I called the police too. I said, I know that you're coming to arrest me and that I can't talk my way out of this. Like, what should I do in order to make sure that this is a pleasant experience for both me and the gentleman coming to take me away?
Did you get arrested?
Yeah. It's a lot more boring than you think it would be. It's like being
But
taken
doesn't
to
the company like hire you to do that?
But the company that doesn't know me, see, their boss talks to my boss, and then my boss sends me out. See, part of it is if they knew me, then they would be able to stop me.
But the boss doesn't even know.
The boss doesn't even know
Okay.
me, so then, yeah. I mean, I got out pretty
We're
quick.
talking about like arresting being boring.
Being arrested is being boring. Yeah, it's well, unless you're belligerent about it. I mean, it can get exciting that way. But
I thought this was America.
That's right.
Fighting people.
No, but I mean, like it's being handcuffed is uncomfortable, but then you go and you sit in a holding cell, which is like just a waiting room that you're not allowed to leave. That's basically what it's like. And you're in there with other bored people. That's the best I can do to describe the experience. And then the other part of it was to get the arrest expunged from my record. I had to sit in court for like 12 hours until it was my turn to.
You were just doing your job.
Exactly. Okay, anyhow.
So we were like selling that data you got.
No, it was auditing company security systems. So we would try to penetrate their networks, and we would try to do on-site penetrations, and we'd test out their things. Sometimes it was quite humorous, the stuff that we managed to get them to do. So we're looking for holes in procedures is the big one. Like one company, I just kind of showed up and said, "I'm your new tech," and they gave me credentials and a desk, and I worked for them for about like 6 weeks. And I even serviced tickets and stuff. I fixed people's computers and internet connections and things, but I was stealing data from the company, and I had all of it, like the entire company's data by the end of it. I had duplicated their entire backup array, which had copies of every hard drive in the building. Yeah.
Incredible.
How much storage do they have?
Well, this was in the early 2000s, so about like 2 terabytes.
Oh.
But it's spread over 26 hard drives in a RAID array, a hot swappable RAID array. So what I did was I purchased 26 of the same kind of drive.
RAID
And
5?
Yeah, it was RAID 5.
Oh, okay.
And so every day I would go in and I would swap out one of the disks and just take their original one home. That's what
It
I was
fixes it
really doing.
automatically. There's no manual fixing.
Yeah, it builds itself automatically. It logs the time that a hot swap took place. They happen all the time over the course
So
of
are
a
you
normal
stealing
week.
Pellissippi's data right now?
Could
Like, you're
be.
not actually a professor. just you're acting like one.
Yeah. All right. So maybe.
He's got
You
a
never
point.
know.
That's why I waste so much time telling stories.
That's right. So they still think I went to college. Ah. No. Okay. That is a useful skill in grad school, though.
What?
Being able to lie with a straight face. It really helps in data analysis from time to time. To gloss over details. It's like, but what about over there? No, you don't need to see that part of the graph. That's boring. Let's go look at this. Okay, so now we know what hashing is, sort of. If we think about a hash table is actually made out of three things. Now, the book says it's made out of two things, but then one of the things that it says it's made out of actually has two parts. So it's really three things. So, if we have a hash table, what we have is we have a bucket array and we have a hash function. And what the hash function does is it generates, hash codes. And then we have a compression function. And the compression function translates hash codes into indexes. So if you have those three things, you have yourself a hash table. Now there's two operations on a hash table that we're interested in, but there's actually three operations that we should describe. And those are insert, to put something in the hash table. And maybe we shouldn't say insert, because that implies picking a position. And that's not how these things work. Let's say add, to add things to the hash table. Your book calls it insert. I don't like that. If I'm inserting, I think I'm saying, at this position, put this thing. That's what insert means to be. To a hash table, you're saying, add this to the hash table. And it goes somewhere. So there's add, there is find, and then one more, which is rehash, which we'll talk about rehashing here in a minute. I've always thought that rehashing, I could make some kind of analogy with a hibachi chef, but I haven't worked that out yet. It came to me one day when I was at one, and they're chopping things. There's some joke about rehashing here, but I haven't found it. I've been thinking about it for about 5 or 6 years now, but eventually it'll be good. I got a feeling it'll be good. So, you want a picture of that before I?
You good?
Okay. So here's the basic idea for how we generate indexes for a hash table. When we insert into a hash table, it'll work like this. We'll get a hash code. So so we want to insert some x. And here's the generic idea of what we're going to do. We're going to say that h is equal to whatever the hash function is of x. So we're going to hash x. And then we're going to say I is equal to compress I. And I called it insert again. Add. And then, so I'm going to compress. And then I would take my table, or my buckets, and I would say like bucket sub I is equal to x. Now this is the idealized version of what happens. When we have collisions, that's where things begin to become a problem. Okay, but if every single thing we would ever insert into the hash table turned into a unique address, then this is the way we would do it. And clearly that would be an order 1 algorithm. Okay, so this is the ideal. And it is big O of 1. It's constant time because I just compute 2 numbers and then slap the thing in there. Done. And then find. Again, the ideal find operation looks like this. We would just say h equals hash x, I equals that should be compress H, sorry. Compress H, and then return buckets of I. Now maybe returning the item from the bucket, maybe the bucket can tell me if the item is there or not. And if the item is there, then we've just returned it in constant time. And if it's not there, we've returned the data structure that will tell us it's not there in constant time. So it's not bad, right? It's a pretty good thing that we've got here. So this would be, again, ideal, and it would be order. It would be big O1. Of course, the ideal is not realizable. I would have to somehow guarantee that that I never had a collision, that my function would map precisely to where I had this. Now, I might be able to guarantee that. If I'm hashing integers, one simple way to ensure there are no collisions would be to just return that integer, right? 1 becomes 1, 2 becomes 2, 3 becomes 3, and so on. And then if I were to make sure that I had an array that had enough space to contain one of every integer, then I'm golden. So, allocate a nice 4 gigabyte array, done. But that'd be about the only time I could really make that guarantee. So what prevents us from being able to do this is we actually have to do something a little bit differently. We have to handle collisions. So let's talk about handling collisions. And there are different ways that this is addressed. So in a hash table, if two items want to occupy the same space, the same slot, or same bucket, this is a collision. Okay, so there's a variety of strategies for dealing with these collisions. There's two main strategies, really, for dealing with them. Well, there's two categories of dealing with them. One, there's two main categories, or two main categories of solutions. There are different ways to carry out these. First is this thing called chaining. And then the second is called, your book calls it open addressing. And your book is the only book where I've ever heard that term. I've read a lot of books on this, on data structures. So you'll more commonly heard this referred to as probing. Okay. So we're going to talk about these each in turn. And so we're going to start off with chaining, and then we're going to use that to introduce some scary sounding words, scarier sounding words. And then we'll see that they're really not at all. Oh, and it even has a Greek letter. We get to use a Greek letter tonight.
Ooh.
Yes.
Which one?
Lambda.
Oh, my favorite.
But we're not going to use it in the scariest context. Alonzo Church gave lambda its scariest context, and that's not what we're doing. Oh yeah, I wanted to check. Hey, that's still correct.
Yeah.
Huh?
I saw that earlier. That clock has to be fixed then, right?
Yeah, but it's like updates itself every 5 seconds.
I wonder if that just happened accidentally.
It like sits there and
That's
then.
distracting.
Yeah.
I'm glad I'm not facing that way.
Yeah, I had fun on. It was Tuesday after you all left. I filmed that, and then I also flipped the switch and pushed the buttons on that thing. I've always wanted to do that.
What is that thing?
What'd it do?
It's an air conditioner.
I've never noticed that.
I've never seen that.
I haven't figured out the purpose of the air conditioner though, because it pulls air in from the left-hand side and it blows it out the bottom of the right-hand side. So I'm not sure what it's meant to accomplish.
All right.
And it's very loud,
Weird.
and it has alarms. But they
that's
don't-
not an air conditioner.
How-
That's an
That's
air
funny.
conditioner.
That has some kind of clandestine purpose.
Well, I don't know, but I turned it on and it's an air conditioner. And then I pushed the green button and it turned off. And I pushed it again, it turned back on, but with a bunch of alert lights, and I pushed the yellow button and it cleared all the alarms. And then I turned it off and left.
Nice.
Yeah.
Huh.
It's my most viewed going live moment.
Every time you hit the button.
Now that just leaves the big red buttons. Oh, I know what they do though.
Do you have to press them other ones?
No,
That's good.
pressing just one will cut power to the entire building.
Why?
I don't know, I haven't figured out that part of why we have that capability. But we have an emergency shunt cutoff that will disconnect the main.
I can see it in some of the engineering, like they got some crazy stuff going on downstairs, but.
Yeah, maybe there was like machines up here or something, but don't push them because it actually turns it off in a way that requires an electrician to bring it back.
They shouldn't have made it.
They also have them at West Town Mall as well.
Really? Where?
They have them by the restrooms,
Yeah.
and then also over where the security office is, and then there's another one at the other end of the mall, like on a random pillar.
So would the camera shut off if I hit the button?
I don't know. Everything else would,
Okay.
so they're probably on battery.
I'm just curious.
Okay, so here we go.
I'm asking for a friend.
Let's talk about chaining. So here's what chaining is. The essential idea is that each bucket slot
Yeah.
is a linked list.
I think I followed.
So suppose we had this situation. So we're going to say that this is going, I'm going to generate just some random things. So let's say suppose we had some hash function. We haven't talked about how to construct the hash functions yet, but suppose we had a hash function that did this to us. We had strings, and then we had the resultant i's. I'm going to put like cat, dog, and bird. And cat went to slot 1, dog went to slot 2, and then bird also wanted to go to slot 1. Now there's a collision. Well, in chaining, what would happen is we would have a bucket array that would have some size. So we would have this kind of scenario. And when I would insert things into this, I would come and I would insert cat. And so I would put a node here where I would have cat. And then I would insert dog, and dog would get placed here. And then when I inserted bird, I would come to this slot and I would put the bird at the end of the list.
You mean on cat?
Or sorry, on cat, yeah. So this would be null, this would be bird. And so I can carry this out indefinitely, right? And it does save me something, because as soon as I go to one of these items, then that will tell me what the, that will give me a list that is shorter than the one that I started with to search. Because what I would do is I would, in the chaining scenario for adding, I would add an X. I would do H equals hash X. I equals compress H. And then I would say that I would append to buckets of I the value of X. And that's not an ideal way to do it. That is the chaining way. This is a realizable algorithm. Adding still takes place in one step, effectively. If I maintain a pointer to where the end of that linked list is, if I maintain where the tail is, or maybe I always insert at the head, I can do that too. I don't have to maintain anything, I just maintain the head pointer. But anyway, I'm going to add it to the list. Done. And then if I wanted to find something, so if I wanted to find x, well, what I would do to find it is I would just say h equals hash x, I equals compress h, and then append, or not append, I'm searching for it, so then I would say for PTR equals bucket sub I, and then while PTR does not equal null, then I would do PTR equals PTR arrow next, and then if star PTR is equal to x, then I would, or equal to, I would say star PTR's value is equal, or sorry, I should really do it this way. If PTR's arrow key is equal to x arrow key, for instance. So if the pointer's key is equal to that key, then I return the pointer. Or maybe I return pointer's value or something. And then that's the end of my for loop. So this is my if, this is my for. And then otherwise I would return null. So this thing's linear in the size of these lists. We can't really determine how much runtime this will actually take because we don't know how the hash function has distributed things throughout the bucket list. And so we need some way to identify that. We can't make an asymptotic assertion about it because we can't really ever analyze a hashing function over the entire domain of all the keys that it might encounter. That's usually not practical. So what we want to do is we want to determine what's called the loading factor. Okay, so the loading factor is this. The loading factor, we take n, which is the maximum number of elements in a bucket. That's one way to put it. Actually, how's the book phrase it? Let me see what the book's phrase is. I'm going to use the same phrasing the book does. Right? It said there is imprecise. We'll open up our textbook like good students. Everyone's been reading it, right?
Oh yeah.
Well, of course.
All the way through.
Okay. You should.
I started with the
It
introduction.
didn't cost enough.
Footnotes.
Or at least the time you invested in it to find the PDF of it took some. I get all the books I want for free.
Oh, that's nice.
That's because they know that I'll sell them. I'll sell it. Like, if I like a book, then I can instantly sell 30 copies of it. That's why they'll let me have whatever book I want for free.
Do you like this book?
It's okay.
Alright. What's a better book?
I like the one, well, I might be heavily biased on this, but I like the one that my colleague at Marable College wrote. It's called, I forget the name of it now. It was going to be called Just Enough Data Structures, and now it has some kind of, like, not cool sounding name. It's small, it's very small. Doesn't cover all the stuff that we're covering, though. Comes close. Come on, mouse. Real quick here. You go to Amazon, you search for Lee Wittenberg. You'll probably find it. Yeah, there it is. Data Structures and Algorithms in C++, the Pocket Primer. It's a little bitty book. Very nice. But see, like I said, I might be biased because I helped proofread this thing. Although this publisher made him take away all the fun stuff. But you see what he covers in there. So he covers algorithm analysis, linked lists, stacks and queues, recursion, binary trees. He talks about self-organized or self-correcting or self-balancing trees, but he doesn't really implement them in it. Sorting, he talks about sorting. He has a nice chapter on hash tables, very nice chapter on hash tables, in fact. And then he talks about graphs, but he doesn't include the ABL trees for us. But as you can see, it's also reasonably priced. I like it. All right, so let's see. I think I must have looked at the Q's section most recently. Let's see what it says about hash tables. I do want to be at least a little bit consistent with its definitions. It drew buckets for you, I didn't draw buckets.
What do you?
You're like the low factors, it says 386.
I work in the IT department.
Like 8 pages ago.
You're like an assistant.
Or it's on like the left side there.
No, I work in the IT
On
department.
the
You work there?
the left side, there's
Yeah.
load factors and rehashing.
Where?
On the table to the left of the actual
Service, the
Can you see that too?
computers,
Oh,
phones,
yeah.
and
Yeah, there you go.
like mobile phones and desk phones.
Okay, well, basically the same thing. Let me see if I can phrase it better. Yes, the lambda's going. It's not the max number. Really, it's the same as the. So n is the number of items in the table. There we go. I like that. They also use the number of items occupying a bucket, so the number of buckets that are occupied, the number of items that you've inserted. Every time you insert, you increment little n. And then there's capital N. And this is unfortunate, but this is also the standard. Capital N is the capacity of the table. The value lambda is just n divided by n. Little n divided by big N. The percentage of the hash table that is filled.
Okay.
Now, what that would tell you is it would tell you an expectation about the hash table. So a full hash table, so a hash table that's at capacity, so lambda equals 1, would be filled, and this would be bad. This is the point where it degrades into linear search. Okay, so this would be like doing a linear search. See, one way that you could kind of sort of think about it is that add and find. I'm not even going to put approximation. I'm going to use this phrase, are kind of, sort of, big O lambda n. Kind of, sort of. So lambda times the number of elements in the array. So at 1, it becomes a perfect linear search. At 0.5, it's 0.5 n. It's like half a linear search. This isn't really precise at all. It's just kind of a way to think about what this heuristic is. Now, the actual pursuit of what the expected number of lookups are, or the expected number of things that you actually have to traverse and compare, is actually a lot more nuanced than this. But this is sort of like the upper bound of it. Will be the loading factor times the number of elements that are in the hash table. And then this is where we have to kind of look at experiments for this. And it is basically that with this sort of thing, with this sort of chaining, or with chaining, then we want to maintain a lambda value that's less than 0.9. It's got to be less than 1, but how much less than 1 depends on what you have. So then for this one, we have a goal, which is to keep lambda less than 0.9. Why 0.9? Because a large-scale hashing experiment, where they just kept on hashing lots and lots of values, found that 0.9 is the tipping point for chaining, where it becomes no better than linear search. So once you hit a 0.9 loading factor, then you want to carry out a process called rehashing. Rehashing is a little bit expensive when you do it. It's a linear time operation, but it's not that difficult. And rehashing will basically work the same way no matter what you do. So I'm going to write a rehashing algorithm over here. And this will be the same regardless of which way we choose to implement our buckets. So let's say we're going to rehash the table T, or do T.rehash if you prefer, but we're going to rehash. What we do when we rehash is we allocate a new bucket list, usually with twice the capacity of the current bucket list. If we make it twice the capacity, we cut our loading factor in half, right? So if we've hit loading 0.9, then we'll approach loading 0.45 next. I mean, you get that for free. It's not all that advanced math. And it will take a while to fill back up. When we rehash, we're going to say that our bucket, our new bucket list, is going to be a new array twice as big as our old one. That's the first bit. And then after we do that, I don't know why we decided bullets would be appropriate there. We make a new array that's twice as big as the old one, and then we say for every item in T, we just do insert item. Done. We reinsert all of our items. It's a linear time operation. Same type of operation as it would be if we expanded the capacity of a vector. It's a very practical thing to do. It's really not that hard at all. Okay, so that's my rehash algorithm. So we can add it to our things, and we can notice that this operation is big O n. So that means that as the hash grows, and we start to approach something that's going to move away from our ideal. Remember, our ideal is constant time inserts and lookups, right? Well, then we have, for our ideals for that, we want to stay close to that. If we stay below our threshold of 0.9, we get that kind of behavior. But then once we add that last element, that would cause us to go over the mark. Then we rehash the table. We do exactly one linear operation, and then we're back to having constant time operations again. So it's very, very efficient. And because it's a doubling operation, it takes a logarithmic number of times doing that before we have an optimally sized hash table. So in general, it takes log n time. So we're looking at like n log n to build a hash table. And then we get the ability to search it very quickly. And that's why maps usually use hash tables. In fact, if you decide that you want to go program Java for some reason, you'll find out that Java does not have a map. It actually calls it a hash table. Same thing, though. And of course, all of us old coder types would be like, yeah, it's hash table, no problem. We look for those two words, like, is it going to be a hash table or a map in this language? Oh, they call them hash tables, we're going to use that. Oh, look, map, we'll use that one. And then we make fun of Python because it calls it dictionaries, just to be different. The dictionaries are a hash table.
And a map.
So a hash table is an associative array?
Yes, that's its most common usage anyway. It's also incidentally used in the C compiler. If you build a switch statement is not the same thing as doing an if and then comparing a bunch of times. a switch statement actually builds a jump table, which is a type of hash table generated by the compiler, which was originally intended as being a sort of optimization technique, so that you could, when you knew that you were going to do something that could be done by jump table, you do it by jump table and then you produce faster code. Now that doesn't matter, because the compiler will oftentimes generate those for you automatically. The reason it still exists, though, is because that syntax has stuck, and because in some situations it feels like the more correct way to express what you're doing. Like if you have a menu, a switch feels right, even though it's actually more typing than the if. People think it's less typing, but unless you've made a variable that's like 7 characters long, typing case over and over again quickly outstrips typing if in 2 parentheses.
Yeah, but you don't have to hit the shift key.
Ah.
Actually, you do, because you have to use a colon.
Yeah.
Never mind.
But only once, though. It doesn't save you much. But in some cases, it makes your code clearer, and so it's okay. If you abuse it, then it's bad. So, you ever seen The Abuses?
No.
Don't ever do this. It's called the duck device. Duff's device. It's on Wikipedia. It must be good. Yep, that's it. Right there. It unrolls a loop. So each iteration of this loop does 8 iterations before it does one compare. Unless, of course, it's something, so it does 8 at a time until it gets to the one that's not divisible by 8, and then it only makes it through that far in the case statement. Notice that the while loop is interleaved with the switch. So the do is at case 0, and the while is after the case 1. And there's no breaks in it. So what will happen is it does mod 8, and if its remainder is 0, then we enter a do loop, and then we fall through all of these, meaning we did 8, and then we subtract from in, and then we go back up to the top here, and just keep on doing that. It actually is faster on some compilers. On like the old school C compiler, this would actually result in faster code than simply building a while loop that would copy that memory. But on modern compilers, it's actually slower because the optimizations that the compilers would apply are actually better than this. They produce something even more cryptic. Actually, a lot of times what modern compilers will do, because most modern hardware actually has a faster way to copy memory blocks. Like the i386 has this really nice one where you tell it how many blocks you want in one register, and you tell it the start and the finish, or you tell it the start, the from address and the to address, and then you let it go, and then it copies 1 byte per clock cycle, which is a lot faster than you could copy it in a for loop. And so most of the time compilers will realize that's going on, and then it will generate that code instead. But if you didn't have that, Duff's device does have its place, or did have its place. Mostly it was something for programmers to chuckle at. Anyhow, we've got rehashing, we've got that, we've got find, we've got chaining. So let's talk about open addressing, or probing. I am going to call it probing. Probing. So what this is instead of chaining, so we don't chain. Each bucket contains just one item. No lists. So that's the first bit. So that begs the question, what do we do about collisions, right? Well, if there is a collision, we do one of the following. We could do a linear probe, which would be a linear transformation of I. Or let me say it this way. So while there is a collision, we'll do a linear probe, which would be a linear transformation on I. Or it could be a quadratic probe. So this would be a quadratic function is applied. Or we might do a secondary hash. So this would be an H prime function on the original data set. Now, of course, that runs the difficulty of how do we build a secondary hash that might explore all buckets eventually. So this one is of them hardest. So this is harder. I'll say that really this thing right here, linear probing, is the one that is probably the most common form. It's even more common than doing it's even more common than doing chaining. Chaining is rarely done outside of computer science textbooks. I know whenever I've wanted a hash map and I didn't just use the one built into the language, I've always implemented either linear or quadratic probing. Quadratic probing is useful if you know the data are going to be sparse. Okay, now no matter which one of these you choose though, with any kind of open address scheme or probing, you want to maintain a lambda value that is less than 0.5. Okay, so they degrade a little bit faster, but they are a little bit easier to implement, and they'll use up less memory because they don't have that external data structure to contend with. Okay, so here's what add looks like in this. So if we're going to add an x, then we do our familiar h equals hash on x. I is equal to compress